Hi, my name's Mike Fiedler, and today we are going to cover material models, an overview. I'm one of the designated support specialists at Autodesk, and I'm going to work with you on today's topic. We will be taking a look at the material models that are available inside of Autodesk Inventor Nastran. So let's go ahead over to Inventor and get started. Alright, so here I am inside of Inventor Professional, and I created just a simple surface geometry so that way we can go into the Nastran product and begin to take a look at a couple different things, and then later we'll be moving on to a solid model to take a look at a few other things with the program. So let's start with our surface model here, and what I'm going to do is just go to environments, and then I will select Autodesk Inventor Nastran. And since we have a surface model, what I'm going to do is create a new idealization, and we will tell it that these are going to be shell elements. Now, if you come in with some thin CAD geometry, you can use some of the tools here, the offset surfaces, the fine thin bodies, and you can extract the mid-surface out of that geometry, and as the program does that, it will automatically determine and fill in the thickness here for you for your different geometries. But in this case, since we're starting with something that is just a surface model, I would need to tell it what the thickness is, but I guess neither here nor there. That isn't the focus of today's particular topic. But let me go ahead and just define that thickness. And the whole reason I'm doing this, defining the idealization and giving it some thickness, is because I want to generate the mesh so that we can see what the elements look like, what the mesh looks like. So there we can see we have a somewhat random mesh on it. It is mostly quadrilateral. Perhaps I should jump back just real quick into the shell definition. When I created this idealization, you notice towards the bottom left hand corner you can choose whether you want quads or triangles, and I had left it on the quadrilateral, so you see that we have mostly quadrilateral elements. There are probably a few triangular elements. Yes, there you go. And when I created this geometry, it's just a 6-inch by 4-inch rectangle, and then I left two cutouts in it, and that was to kind of try and force some randomness in the mesh, and you can see that we accomplished that because we'll be taking a look at something here very shortly, which this will help illustrate the point. So our focus today is on the material models. So what I'm going to do is access the material. Let me just expand my idealization and say edit, and this brings up the material screen for Inventor Nastran. Now, when you start working with the program, I think you probably have watched a video or two, or maybe you've gone through a tutorial or demonstration or two. Maybe this is the very first video that you are watching on the program. Pretty straightforward, right? There is going to be a density, or you should enter in a density. There's a modulus of elasticity. There's your Poisson's ratio, your thermal coefficient of expansion if you need it. And then if you're going to include some thermal effects, probably want to identify a reference temperature and activate your thermal properties so that you can define the specific heat and thermal conductivity. So this is all fine and well. Your isotropic, elastic material properties, which are perhaps the simplest and most straightforward ones. And there's a lot of videos out there, a lot of tutorials which cover this material model, so I'm not going to spend a lot of time here. We're really talking about what happens when you need to go beyond the isotropic and or elastic materials. So it's perhaps kind of obvious on the left hand side towards the top here. You see the type is set to isotropic by default, and underneath there is where you will find some of the other options, and we'll talk about those in just a minute. But one of the reasons that I'm doing this video, not only to show you a few things about some of these input screens, but beyond that there are some additional places that you need to look when you're entering in certain materials so that you can fully characterize that particular material. One of those is right below the type, and that's right here where you see subtype. And this really comes in with the hyperelastic material, so we will take a look at that as well. And then the other area of importance, I would say, would be down here in the lower left-hand corner where there is your analysis specific data, which includes nonlinear options, which we will take a deeper dive into. It includes your options for fatigue and then PPFA. So really, when we talk about material models or the inputs to characterize the material, it's really, I guess, primarily these three things, in addition to, of course, selecting a material or entering in your material properties that you should be aware of. So let's first of all take a look at some of the things under type. So moving beyond the isotropic, underneath isotropic you have your orthotropic 2D and orthotropic 3D. So that allows you to define material properties in different directions. And that's one of the first things we're going to take a look at here shortly, the reason that we created this simple geometry. And then beyond that you have an anisotropic 3D, which really moves beyond, a step beyond the orthotropic materials. And then you have your hyperelastics. Again, we'll take a look at something there. Nitinol, and then viscoelastic for creep type of materials as well. So be aware that all those different material models or material types are available there underneath that pull down menu. And the reason that I'm driving the awareness primarily is if you just get started with the program, a lot of the tutorials that you find, a lot of the videos that you find are going to deal with isotropic. And why would that be? It's because the vast majority of a lot of people's analysis work can be accomplished just using an isotropic elastic material, and that's all fine and well, but somewhere along the way, as you become comfortable with the program, somebody might say, hey, what we have here is an orthotropic material. Can we handle it? Can we simulate it? Or you might encounter a hyperelastic material if you're doing something with seals or O-rings, things like that. So just to note that these things are available in the software. So the first thing I'm going to take a look at beyond isotropic is the orthotropic 2D. And when we switch to an orthotropic, or when we switch to any different type really here under the material screen, you'll notice that the input fields are going to change up a little bit. So because we've switched it to an orthotropic 2D, you see now that we can define our longitudinal modulus and our lateral modulus, E1 and E2. And then I have my Poisson's ratio. My thermal coefficients of expansion are then determined by directions, or can be defined by direction there, right? Longitudinal thermal expansion coefficient alpha 1 and alpha 2, the lateral thermal coefficient of expansion. And you notice even up here under the thermal properties, then we can define thermal conductivities in different directions as well. So that could be kind of straightforward, right? We could define E1 properties, say, or at least theoretically we want to define my modulus of elasticity, or Young's modulus, in this direction, if this is going to be defined or set up with a orthotropic material. Okay, so you could enter in your properties, E1, E2, enter in your Poisson's ratio and so on to define this. But the question is then, what we're going to expand upon for just a moment is what would be the directions. What's E1, what's E2? So let me cancel out, or I'll say okay to that for just a second. There's an additional step that you should take when you need to define these local material axes. And that's actually out here. If we go to the menu tree, you'll notice there's analysis 1. I can right click on that and I can say that I want to create new, and under new, one of my options there is material orientation. So that is where this will get done. And what I can do is select my material, select my geometry. I was reading this input screen right here, the material orientation one, the name for this particular material orientation that we're defining. But then the means to define it are all available here. So there are about 8 or so different ways in which you can define this material orientation. And it's because the geometry that you have might not always be a nice planar example like you have here. So some of these means might be better in the case that you have some geometry that is more tube-like, for instance, and then some of them are very simple when you have some planar geometry. So with the planar geometry, I could probably just get away with doing something like a surface U direction. And you'll notice that even though the orientation of these elements are rather random, right? Some of them are perfectly or near perfectly quadrilateral elements. Some of them are, at an angle or shaped kind of differently. But when I define a surface U direction, now that shows me that the material axis is now all basically off in the X direction. So then I can define the material properties in the one direction, and then orthogonal to that in the 90-degree direction off of that axis, right? And then you have the V direction, so I could change it to the vertical as this model is oriented, and then you have the negative options compared to those two directions. One of the things that I think is probably most useful here is a vector projection. And when you go into a vector projection, what that allows you to do is to input X, Y, and Z inputs here, which define the endpoint of an orientation vector. So imagine that the first point by default is going to be 0, 0, 0, and then I can give it the endpoints of that vector. So if I give it something like 1, then you can see 0, 0, 0 to 1, basically 0, 0, then puts all the material orientation or all the material axes off in the X direction, right? So I think that makes sense. If I make that 0 and I make the second field Y, then 0, 0, 0 to 0, 1, 0, then the material axis is all off in that direction. So why am I showing you this one specifically? Well, it might not be the case that your material is oriented perfectly with the x-axis and the second direction is perfectly off in the y-axis. You might have something where, well, if it's something like a composite, it might be at a 45-degree angle. Your fibers, if it's a long fiber composite, the fibers could all be at 45 degrees with respect to this geometry, and then the other axis defined as 90 degrees to that. So in that case, we could do something like 1x and 1y, and now you see that everything is off at 45 degrees, and then orthogonal to that would be my other properties. Okay, so that's one of the things that I wanted to show. So just be aware that when you utilize some of these other material models like the orthotropic, really, you might need to subsequently define or should subsequently define some additional information beyond just what's here in the menu screen. Now, as we go down the list, of course, anisotropic is a little bit more elaborate than the orthotropics, or advanced than the orthotropics, as I mentioned, different properties in all different directions. So something like this material model requires you to define the material property matrix, and this is no different than some of the other finite element analysis packages that I've utilized. Might require a bit more work in order to find the material properties to input there. And by the way, I should note that we aren't going to spend a whole lot of time on some of these other material models. I would say that two different things. One, if you do need to get into it deeper, I guess three different things. If you do need to get into it deeper, you can always hit the question mark, which will take you to the relevant area of the documentation. Second thing is that you can always, talk to a specialist when you're on the phone with them. And then the third thing that I would say about that is, some of these are rather involved in their setup. So my intention is that hopefully in the near future we can do some additional content and we just focus in those videos on some of these specific material models, because to do them all within a single one that isn't just an overview would make for a very lengthy webinar presentation. So off the top of my head, I know I'd like to do something with hyperelastics coming up. I'd like to do something on viscoelastic. I'd like to do something on fatigue. But again, today we'll do an overview, and then I'm going to focus on nonlinear. But for now, I'll just show you some of these other inputs. So nitinol, a shape memory alloy. You can certainly do that with the program. And I would also note that when you choose some of these other material models, note that the pop-up comes up here that says you need to run a nonlinear analysis in order to utilize this material model. And I think that makes perfect sense as well. So if we go into viscoelastic, same thing. You need to have a nonlinear analysis in order to perform this type of analysis. And again, hopefully we get to do a webinar on, specifically on these material models in the near future. So just to be aware that the software will accommodate these different types of material models. I do want to take a look at something with the hyperelastic. So when we go into hyperelastic, I guess two different things that I want to talk about with the hyperelastic materials. And the hyperelastic materials, they're going to be used for some, like a rubber-like type of material where potentially on the stress strain curve there is no linear portion to it whatsoever. What I would say about them, usually they are temperature dependent as well. So you need to consider that whenever you are inputting your material properties. At what temperature is it operating, and at what temperature did the material properties get captured? So just another thing to consider. But two things I want to show with this one. First of all, there are different subtypes, right? So that's when this subtype menu comes in handy. So there's the Neo-Hookean, there's Mooney-Rivlin, the EO model, Ogden model here. So depending on which material constants you have, that could very well dictate which subtype you are going to utilize. And the different material models do have some different limitations to it. So Mooney-Rivlin is good up to a certain percentage of strain, and then Ogden came along and said, hey, I can characterize this using this equation and these coefficients, and it's good for a much greater range of strain. So just be aware of that and which constants you're dealing with and so forth. The second thing that I would say about this is with a lot of the subtypes here for the hyperelastic materials, you'll notice that you have your experimental data function over here. So instead of just finding the constant, and you can find some of these constants on the web. So if you look for Mooney-Rivlin constants, for a specific material, if it's a common material, there's a good chance that you're going to find the constants, or if you speak with the material supplier, there's a good chance you can get the constants from them. When all else fails, there are companies which will test these materials for you. And they're going to put the materials through a certain set of tests. They can test it in simple tension or compression. They can do equibiaxial tests. They can do simple shear tests. And when they do these different tests, they can do them at different temperatures, or at a temperature that you say that this is going to operate in. And then they can provide the data for you. So I have a sample of one of these. Let me just pop over to my Excel spreadsheet. So these are the results of a equibiaxial test that was done by one of these companies some time ago. And so I have my test data here, and basically they come back with X number of Excel sheets. I have a separate Excel sheet for tension data, and a separate one for equibiaxial, and another one for volumetric in my case. So I have my test data, and what we can do is check the box here and say that we have equibiaxial tension. So the reason I wanted to show this is because on some of these material model input screens, you'll notice that there's a little dialog to the right, and in this case it shows up once you check the box. And what that means is you can import data. You could either type in the fields or you can import data. So if I go ahead and I click that, I can see there's my input fields. So if I go back to my data, right, let me pull up my Excel sheet here. What I'm going to do is just highlight these rows. Nothing too super crazy here. I have all those rows highlighted. I'm going to do a Control-C to copy. And then again, come back here. And I can do a Control-V to paste. So that just pastes all the data into the table here. And it even has a Show Plot button, so that when I do a show plot, I can see what that looks like. Alright, there we go. So there's my experimental data. You can see the stretch ratio versus the engineering stress. So just be aware of that. And again, you know, if you are doing hyperelastic materials, again, hopefully we'll do a webinar on it. But you can read in that data, and then you don't necessarily need to put in the coefficients there. The program will leverage or calculate it based on your input data. But again, keep your eye out for these types of boxes, which means that you can enter in data in a table. So that was really the goal of what I was going to illustrate there. So I think we briefly talked about all these. Again, isotropic is probably the most common. Orthotropic, make sure that you define your material axis. And isotropic, going to be a little bit more work there to define the matrix. Hyperelastics, you know, used every now and again. I wouldn't say it's one of the most common ones, but you can certainly import the test data, so that's always nice. Shape memory alloys can be done, and then if you are analyzing, you know, something for creep, you can do that with the viscoelastic material model. Okay, and then again, the subtypes apply to the hyperelastics. Now the next thing that I want to take a look at is the bottom section here, and that would be your analysis specific data. And we're going to roll over to a different model for that one. So let's go with this model. And the reason that I have this solid model here is because I was targeting a specific stress result, and that will become apparent here shortly. So let's go into environments, and let's move this one into the Inventor Nastran space. So because I have a solid here, it already has the idealization of a solid. Let's edit the material. The material that I'm going to choose, select the Autodesk material library, and I'm going to choose a steel, and it's an ASTM A36. Alright, and we'll say OK to that. So that brings in my modulus of elasticity at 29E6, Poisson's at 0.3, and because it's an A36 material, we know it has a yield stress of 36,000 and a tensile limit of 58,000. So let me explain the geometry a little bit, and I will upload a model of this to the data set. If you do want to pull that down, you can certainly do so, but if you are not within the finite element analysis journey, if you're just watching this video, say on YouTube or something like that, and you want to reconstruct this geometry, I'll tell you the dimensions are 1.5 inch high. It is 4 inches long, right? So 1.5 by 4. The thickness then extruded at a 1/2 inch, and then right at the center along the length we notched it out, and the radius on those notches is 0.45 inches, or 0.9 inches in diameter. And again, I just defined it as an A36. So initially we're going to run this as an isotropic, and then we're going to show you one of the limitations of running it as an isotropic, and ultimately we will run it as a nonlinear. So that will be our focus. And the reason I am expanding upon this one in this presentation is, again, normally people start with isotropic elastic materials, and then one of the first things that you'll encounter when you need a new material model is because of exceeding the yield with an analysis. Some damage is going to be experienced, some permanent deformation, and you need to obtain appropriate results for that type of analysis. So that's when we leverage the nonlinear analysis specific data. Okay, but also down here there's two other options here. There's a PPFA, and that's progressive ply failure analysis. You can tell it that you want to perform those calculations, and you enter in your reduction scale factor for Young's modulus and reduction scale factor for shear. So that's also here. And then the other thing that's here beyond the nonlinear would be your fatigue. So we accommodate two different types of fatigue. There's your SN data, or your stress-based fatigue that can be done. The inputs here are pretty straightforward, right? They just correspond to the graph. You can input your slope right there, your intercept stress level S sub u, the intercept cycles, your reduction effects, and so on. And basically you're inputting this curve, and you can perform a fatigue analysis. And it also accommodates strain life data as well. So stress, life data generally used for high cycle fatigue, and then strain based whenever it's a low cycle fatigue problem in general. But again, hopefully we do a presentation on that in the near future. I would mention that a colleague of mine did a fatigue based AU course a few years ago. So if you're familiar with Autodesk University, you can Google Autodesk University sessions and then search up fatigue and Nastran. You will find the presentation that one of my colleagues did. You can download the paper that accompanies that, and even listen to the presentation. So that is currently available. So again, with this deep dive, our focus is going to be on nonlinear, and I'm going to come back to the nonlinear effects in just a little bit. We're going to start with this as isotropic elastic. Keep in mind that the yield stress here is 36,000 and our tensile limit's 58,000. So let's go ahead and set this up. What I know I want to input here is I'm going to fix this back surface here. I'm going to go ahead and define that as being fixed. And then at the opposite end of the model, we're going to apply a pressure load. And I want that to be a tensile pressure load. So we'll select pressure. So my magnitude is going to be a -1000 psi. And of course that will be in the positive x direction. And the reason that I'm doing that, let me just go ahead and preview this and increase the density a little bit of those arrows so we can see it. All right, there we go. The reason I'm doing that is because I'm looking for a particular result with this particular geometry, this particular pressure. I'm looking to achieve stress results right around 3000 psi, right? So we know that in order to exceed the yield or to reach the yield, if we do about 12 times that, we should reach the yield of our material. Let's set up our mesh settings. So in mesh settings, I'm going to go ahead and mesh it at about 0.1 inch, and we'll generate the mesh. Now, because it is a notched specimen, we know that we have introduced a stress concentration, right? So our high stress should occur right within the region of this notch. And if I zoom in here, you can see that the mesh doesn't follow it perfectly. If I want to refine that a little bit, what I can do is go into my settings, and when I go into the advanced mesh settings, I can say project midside nodes, and I'll say OK to that, and I'll generate the mesh again. You'll notice what that does is it moves the midside nodes to the curvature of the geometry, so that way we can increase the accuracy of our results just a little bit. And in particular, again, because we do have a notch specimen, the stress concentration, we know that's where our high stresses are going to occur. Say OK to that. Alright, so we have our constraints on the one end of the model, we have the load on the other end of the model, our 1000 psi, and again, my goal here is to try and achieve a stress somewhere around, stress in the x direction should be somewhere around 3000 psi. So that's what we're going for. So what I'm going to do here is come over to the subcases. I'm going to right click on the subcase and I'm going to say I want to duplicate it. So that copies my loads and my constraints. I'm going to rename that. And now what we're going to do is edit the load here. And I just want to edit the load for subcase 2. And keep in mind that if 1000 psi gives me around 3000, what happens if I do something like 20 times that? So we'll go ahead and enter in that load. Let's say that we make it minus 20,000 psi. Okay. And at that point, I have my two different loads, right? In subcase 2, my load is minus 20,000 pounds, and the load in subcase 1 is 1,000 pounds. And at this point, I'm going to go ahead and run the simulation. Okay, so my analysis has completed. We'll say OK. And what we want to take a look at is not subcase 2 to begin with. I want to take a look at subcase 1. There are the von Mises stress. We can see the von Mises is right around 3,000, and we can change it so that we're taking a look at X normal stress. And there I can see my X normal stress is right around 3,125 psi. So that was what we were targeting as far as the stress in this particular model. Okay, and then for our second subcase, we made the load on this model 20 times larger. So if I go to the pull down menu here and I say let's look at subcase number 2, right, there is the solid X normal stress result for the second subcase, and we can see the results are about 62,492, right? Interesting. Obviously we went 20 times the load, and what we see are the stresses are about 20 times what the results are for subcase 1. So interesting, but also wrong, correct? We know that the yield stress on this material is 36,000 psi, and my tensile limit was in the 50 ksi range. So what do we do when we encounter this case? When it comes to a nonlinear analysis and we know that we're going to get near the yield of the material or even exceed the yield of the material. Let's return back to the setup environment. Now what I'm going to do here, we are going to take a look at the nonlinear material properties, but when I utilize one of the nonlinear materials, I also need to run a nonlinear analysis. So I'm going to right click on analysis 1, and I'm going to say to duplicate, and when that comes up we will change the name, and then I need to change the analysis type. So we'll just double click on it, go to the pull down menu, and we can change to a nonlinear static analysis. Go to options, make sure that my large displacements are on. Okay, and now we can go in and edit the material. Okay, so in that first analysis, again, keep in mind that in the second subcase we reached stresses that were 62,000, right? And my yield was 36,000. My tensile limit was at 58,000. So what happened? What we never did was A, we never ran a nonlinear static analysis, and B, we never turned on any nonlinear effects. When I go into the nonlinear, by default it's set to none. And this graph here explains a lot. So what happens with an isotropic elastic is that there, even though on that material input screen there might be a yield stress shown, when it's calculating the stresses, it still just follows the modulus of elasticity, right? So perhaps the yield point is maybe right about here, if you're envisioning an A36 stress strain curve. But when it's calculating the results, it's just going to continue up the slope defined by the modulus of elasticity. Okay? There are a couple different types within the nonlinear material data here. So if I go into a nonlinear elastic, for instance, you can see that what this allows me to do is enter in stress strain data here on the right hand side. So as the graph shows here on the left hand side, you can see that we can have both tensile stress strain data and compressive stress strain data. So you're going to enter in, if you are defining different compressive data than tensile data, enter in the negative values for the compressive data first, and then you can enter in the tensile data. Now, this is nonlinear elastic, so that means no permanent deformation. You're presuming that if you were to remove the load from your geometry, it would return back to a zero strain, zero stress state. But certainly doable to input that type of material data. And I would note that if you don't enter in any compressive data, if you just enter in tensile stress strain data, that is, if you've done, say a simple tension test on it, it's going to presume those same values in a compressive type of analysis. Now, the other two types that are available here, both of these will factor in a yield stress and the behavior post-yield. So what we are going to ultimately use is an elastoplastic bilinear. So I'm going to come back to that. For the moment, let's just take a look at plastic. So if I choose the plastic material model, you'll notice I still have the table over here on the right, so I can enter in values, but I also have some options over here on the left. So first of all, as far as the table is concerned, the first two rows of data define the slope below the yield. You can see that the stress value here in the second row is my yield stress. So again, the change in y over change in x here should be equivalent to the modulus of elasticity. You're not going to want to modify those first two rows. Those correspond to the slope up to the yield stress. And then beyond that, since it now knows what the yield stress is, then you can start to define stress and strain values that define what this curve is past the yield of the material. So that's what this particular type allows you to do. You can define with as many fine points as you would like to define here within reason what that looks like beyond yield. So if you have an Excel sheet, just like we did for the hyperelastic, you can go over, highlight all the stress strain values post the yield stress, and then copy them into this table here. And then if we come over to the left here, we have a couple different hardening rules. There's an isotropic, a kinematic, and an isotropic kinematic depending on what is happening in the model. Generally, the isotropic is the default, which you're going to use just to load a model up, and then kinematic is generally used with something like the cycling of the loads. If you take like a paper clip and you think about bending it back and forth, so you keep passing through a zero stress strain state, or I should say if you're loading it up in tension and then loading it up in compression, something like that. And then you also have different yield functions. You have the von Mises, you have Tresca, you have a Moore Coulomb, and then a Drucker-Prager there. So von Mises generally utilized for metal materials, and then the Tresca is a little bit more conservative when you get into materials that are maybe a little less ductile, a little more brittle. So if you're doing something like a cast iron material. Okay. Now let's go back to the elastoplastic. So this is a simpler version of what we just looked at. You see we don't define the curve past the yield. Instead, what we define is the tangent modulus. So the modulus of elasticity defines our slope below the yield, and then the tangent modulus defines what it is past the yield. And again, it shows us what the yield stress is, and then the tangent modulus it puts in here is 10% of your modulus of elasticity, but certainly you can come into this field and enter it in or edit it appropriately for your particular material. And then you have the same hardening rules and yield criterion that you saw before. So we're going to leave it on elastoplastic and say OK. So again, now we have the yield, we have our tensile limit, we have told the program that we want to utilize the nonlinear data, and we are in a nonlinear static analysis. So I think we have everything just about set up. The only other thing that I would mention is when we switch to a nonlinear static analysis, it does give us this nonlinear setup input. Now normally, if you don't fill in the number of increments for it to solve, the program will determine what it needs as it progresses through the analysis depending on how well it's converging. What I'm going to do is specifically say that we want 20 steps, and I am going to tell it to output all those steps. So the reason I'm going with 20 steps is, remember that at 1000 psi, that's when we're at roughly 3000 psi for our stress, and then we took it all the way up to 20,000 psi as far as our load, which in our prior linear elastic analysis gave us stresses in the 60,000 psi range. So again, because I have a 20,000 pound load on here going 20 increments, then each one of these increments should increase the load on the model by 1000 psi, and we can see how our stresses and displacements change incrementally. So I'm just doing it, so that we have a very measured progression through the simulation when we take a look at our results. Let's go ahead and say OK to that, and we can run that simulation. Alright, I did forget one thing here. Because I did a duplication of my analysis, it did duplicate both of these subcases into the nonlinear analysis. So what I'm going to do here is just delete the second subcase, and we'll go back to my first subcase here. I just don't want you to be following my steps along exactly and have to run an analysis that isn't what you anticipate it to be. So I'm going to edit the load on subcase 1, and we'll just alter that one to be the 20,000 psi case. Let me say OK to that. So now I have just one nonlinear set of data or subcases that I'm going to analyze, and we'll let that analysis run, and then I'll come back as soon as we have results. Okay, beautiful. Our analysis has finished. Here you can see that we are on increment number 20. Remember that I told it to calculate 20 increments. The load factor is 1, or 1 times my input load. And we can see right off the bat that our stresses are lower. Taking a look at von Mises, we're at 41,000 for that 20,000 psi load that we put on here. If we take a look at the solid X normal stress, right, instead of the 60-some thousand that we saw before, we can see that we are about 46,700, and we have exceeded the yield, but we are below the tensile limit of the material. So definitely a pretty significant difference in the results between taking a model past the yield in a linear elastic analysis, which is not ideal other than knowing that you've exceeded the yield, versus the actual results that you would get out of it with a nonlinear analysis with nonlinear effects included. So to go through the different results, if we go all the way back to increment 1, my load is load factor is 0.05 at that point, so 0.05 times the 20. So of course I expect this to be similar to the 1000 psi load that we saw when we ran it as a linear elastic model, and we can see that our stresses are around 3,124. And if we go to load case 2, then we should have around 6,200, right? And we can continue on through, and they're just going to keep adding like that. 9,000, so it's going to keep adding 3,000 to it, because again it's a linear modulus of elasticity, and we said 20 steps, so it's breaking it up in that 20,000 psi into 1,000 psi increments, so I can see nice linear results. And then so my stresses should just increase by 3,000 each time until we get up into the region where the material yields. Right, there's 40,582 at step number 13, and if we go to our next step, 40,582, we go to 42,275. So there you see our change in the stress is only 2,275, and that's a function of the tangent modulus then, right? The slope is not as steep as the Young's modulus, so our stresses are going to increase with the same increase of load on the model. The stresses are going to increase a little bit less than they do in the in the linear range. So you could certainly interrogate the results that way. You could turn on probes and move over different regions of the model and figure out what the stresses are. But maybe the easiest thing to do when you're trying to look at the results or a result over all those steps would be to do it with a graph. So I can right click on XY plot, say that I want to create a new plot, and I want it to be element based since we're going to take a look at a stress, and select one of the elements in that region. On the upper right hand side, I do want it to go across all the increments. I do want it to be the X normal stress, but of course you can graph all the other output options as well. And I'm going to go ahead and say to show a plot. Alright, and there's the plot, and as I hover over different points in this plot, you can see the different steps what we're getting for the output. So there's 35,000 right there. There's our 37,000, so you can see how the slope of that changes once we exceed the yield of our material. So that's what we were expecting and what we hope to get out of utilizing a nonlinear. So again, if you need to take a look at an analysis where you're going to exceed the yield stress of the material with a linear elastic, even though the yield stress might be shown here, it is important that you go into nonlinear, turn those effects on, and utilize one of these other material models or material types that are available here, and then likewise run it with a nonlinear type of analysis. So hopefully that helped you learn a little bit about the material models in general, and then more specifically how to at least utilize the nonlinear analysis specific data. So thanks for watching. Have a good day.